All right, open up your book to section 6-7. This is on page 319 in your book. The title of this section is Sinusoidal Functions as Mathematical Models. And our objective here is given a verbal description of a periodic phenomenon. Write an equation using either sine or cosine function and use the equations as a mathematical model to make predictions and interpretations about the real world. So now we're going to look to use these circular functions and sinusoidal functions to be able to do a little bit of modeling of some situation. And there are a number of different scenarios where we might use a sinusoidal function to do some modeling with. Here are a few examples that the book gives us, and you'll certainly see others as you work on the problems in this section. But one example that they give you is if you were to count the number of red blood cells during chemotherapy. You have a high, and then during therapy it drops down and then comes back up and goes back down. As you keep getting treatments, it keeps oscillating back and forth. You could also measure your daily tides. At some point in the day, you have a high tide, and then later on, you have a low tide, and then it goes back to a high tide, and so forth. Could be that you're measuring the yearly temperature and keeping track of that data. So at one point in the year, you have a high temperature, and at another point in the year, you have a low temperature. Highs in the summer and lows in the winter, and it oscillates back and forth. It's cyclic. And then the rainfall. You could have another example of keeping track of annual rainfall or precipitation, and you have highs at one point, lots of rain, and lows at another point, not as much rain. So those are examples of where you could use sinusoidal functions there to model some real-world phenomena, and we'll definitely be using these for examples just like this. All right, so let's take a look at example 1 there on page 320 in your book. This is a water wheel problem. It says, suppose that a water wheel in figure 6-7b, and that's what we got up here on the board, it rotates at 6 revolutions per minute. 2 seconds after you start a stopwatch, the point P on the rim of the wheel is at its greatest height, which is 13 feet above the surface of the water. And the center of the wheel is 6 feet above the surface. All right, so for part A, I want you to sketch the graph of D as a function of time in seconds since you started the stopwatch. All right, so I guess one thing to note here on this sketch that we've got here, if the radius of our wheel here is 7 feet and it's 6 feet above the surface, then it must mean that we go 1 foot below the water level here. So then in terms of our y-axis, that would be at -1. Our sinusoidal axis must be at 6. And that means that our high point or our upper bound must be up here at 13 if we've got a radius of 3 feet there. That just kind of helps us get started here with sketching this. So let's see if we can sketch this. I'll sketch it kind of right next to it here. That will give us a nice sketch of what this looks like. And it does something like this. This is our time t, which is in seconds, they said, and this is our depth, which is in feet, right? Or height, I guess it is, in feet. All right, so we have an upper bound here of 13. We have a lower bound of -1. And we've got a sinusoidal axis right down the middle of this at 6. All right, so a couple other things that we need to mark here on our sketch. They tell us that 2 seconds after you start the stopwatch, point P is at its greatest, which is 13 feet. So that means that this point right here must be at 2. And then they also tell you that this makes 6 revolutions per minute. And I guess we've got to be careful with that because revolutions per minute is a frequency. If we've got 6 revolutions per minute, that's our frequency. If we reciprocate that, that would be, what, 1/6 of a minute per revolution. Or if we want to convert that over to seconds, since our time interval is in, or since our time axis there is in seconds, maybe we'll do that. So let me multiply that by, what, 60 seconds per 1 minute. We'll just multiply by a clever form of 1 there to do that. So it's 60 over 6. That's 10 seconds per revolution, right? 10 seconds per revolution. That right there is the period. Okay. So with that, the period then from here to this high point is 10 seconds. So this must be at, what, 12 then, right? All right. There's a pretty decent sketch of this. I guess that's part A, was to sketch this. Label that as part A right here. Part A. All right, part B says, assuming that D is a sinusoidal function, write a particular equation. All right, so for part B, they want us to come up with our equation now. So let's find an equation for this. And we got pretty much everything marked on our sketch that we need to do this, right? D of T is equal to 6 plus 7 times the cosine of 2 pi over 10 times T minus 2. So we said, yeah, 2. There we go. There's our equation. And it said confirm by graph for the, okay, so let's grab our calculator and verify that that, in fact, is the right sketch of this thing. All right, so let's just punch this into y1 here. So we got 6 plus 7 cosine of 2 pi divided by 10 times x minus 2 is what we had. And let's set up our window here. Actually, let me, oops, I should zoom 6. Let's get a good window of this thing. Let's go from 0 to maybe the first 30 seconds. It makes a revolution every 10 seconds, so we'll see the first 3 periods of it. We'll set the scale at 10. And for the y's, let's go from like -2 to 14. It actually goes from -1 to 13, but we'll get a little bit extra there. Scale of 1 should be fine. Okay, there we go. That looks like a pretty decent sketch of this. And I guess we could trace this to 2 just to make sure that's when we hit our high point. That looks pretty good there. In fact, maybe I'll grab a picture of it just like that. All right. Part C. Part C says, how high above or below the water's surface will point P be at the time T equals 17.5 seconds? Okay, well, we can determine that. We have an equation now, so we're all set for that, actually. Part C, they're just asking us to evaluate function D at 17.5 seconds and find out what you end up with. Where are we at 17.5? We can probably look at our sketch here. Yeah, actually we can. If we look at our sketch that we've got, let's mark a couple of other points here. We're at our low point halfway between our 2 high points. So that'd be, what, 14 over 2, that's 7 is where we hit this low. 10 seconds later, we're going to hit the next low, which actually is just after the 17.5 seconds. They're asking us to find out what's happening at 17.5. So 17.5 is somewhere about right here. So we should be on our way out of the water, right, is what we should be. At 17 seconds, we hit the lowest we'll get, and then at 17 and a half, we're on our way out. But let's see exactly where we're at. Not sure if we're out of the water yet or not. So let's go back to our calculator. Actually, since we're in graphing mode here, we might as well just hit trace again and go to 17.5. There we are. Grab a picture of that. Yeah, I'll just leave it up there, actually. So So 17.5 seconds, that's a negative 0.657. That would be in feet. All right, so we're 6/10 of a foot below the water. 6/10 of a foot is what, like 8 inches below the water? But we're on our way up. That's what we've determined. Okay, so we're on our way of coming out of the water there. Part D. It says, at what positive time t does point P first emerge from the water? So when do we first emerge from the water? Let me go back to my sketch. And let's look at what they're looking for. When we first emerge from the water, well, we first go into the water, at 7 seconds, we're at the lowest point. So just before that is when we first go in the water. They're looking for this time right here, which is sometime after 7 seconds that we are going to be coming out of the water. So we're trying to find out when our function is equal to a y value of 0. That's the x-axis there. So let's solve this. And we're going to solve this algebraically. This is the way I'm going to ask you to solve these problems here as well, just so we get some more practice. I would assume that we are pretty comfortable with grabbing our calculator and looking at a graphical solution or a numerical solution. It's probably the algebraic solution is the one that we need most practice with. So I'm going to ask that you solve these algebraically. So let's do that. Let's take our equation that we came up with, which was 6 plus 7 cosine of 2 pi over 10 times t minus 2. Let me just double check that I got that written down correctly. 6 plus 7, yes. And we're going to set that equal to 0. In fact, we could even find what value of n we're going to pick here, and whether it's going to be the plus or minus here in our solution before we even go through this. If I'm looking for this guy right here, if you look at your equation here, look at your phase displacement. My phase displacement is 2, so that tells me that I'm starting n at x equals 2. So this is where n is going to be equal to 0. And if I go forward from there, the solution that I hit right here is the solution that you'll end up with using the positive cosine inverse. That's not the one we want. Move forward 1 period. This would be where n is 1. And go backwards. This is the solution you're going to find with n equal to 1, but using the negative cosine inverse. So actually, there's my value of n and the plus or minus that I need. I just need the minus cosine inverse. Now let's go through and find the solution algebraically. All right, subtract your 6. So 7 cosine of 2 pi over 10 times t minus 2 is equal to a negative 6. Divide by 7. Cosine of 2 pi over 10 times t minus 2 is equal to a negative 6/7. Use the arc cosine to rewrite this as 2 pi over 10 times t minus 2 is equal to the arc cosine of a negative 6/7. Multiply by the reciprocal there, so you have t minus 2 is equal to 10 over 2 pi times the arc cosine of a negative 6/7. And add 2, so you get t is equal to 2 plus 10 over 2 pi times the arc cosine of a negative 6/7. All right, now we replace the arc cosine with what it's equal to. So that's plus or minus the cosine inverse of a negative 6/7 plus 2 pi n, because we're in radians here. If it was degrees, we'd use 360 n. And now let's distribute this 10 over 2 pi through the parentheses there. This is going to go here, and this one's going to go there. And what do we end up with? We have 2. I'm going to put the plus or minus out front. 10 over 2 pi cosine inverse of a negative 6/7 plus the 2 pi's will cancel each other out here, and I'll be left with 10n. Again, the significance of the 10n, the 10 is the period of this function. That's what we should always end up with here when we solve this algebraically. And we've already figured out the right solution here, so I don't necessarily need to write this in a piecewise form. I can just simply write down the solution we said. We said from up above, the one solution we're looking for, that's one right there in purple that we got. N is 1, and we're going to use the minus from our cosine inverse there. So we are going to have 2 minus 10 over 2 pi cosine inverse of a negative 6 over 7 plus 10 times 1 is the one solution we're looking for. So let's grab our calculator and see what we end up with that right there. So it's 2 minus 10 divided by 2 pi, and again, make sure your 2 pi is in parentheses. Cosine inverse of a negative 6 over 7 plus 10n, and n in this case is going to be 1, we said. And we're saying that this should be just after 7 seconds is what we are claiming that we're going to get, 7.861. That sounds pretty good. Let's copy that. So we get this is equal to 7.861. And make sure you're including units here in your answers. That should be in seconds, should be our answer. All right, very nice. That is the example that they wanted us to go through. And that's all that we need to talk about here from section 7.7.